Hey guys, all right, so we are on multiplying binomials. So far we've added and subtracted them. Now let's multiply them. So we're going to investigate how to do that by learning how to use a graphic organizer to multiply expressions. We're going to use the distributive property to multiply expressions. Okay. So it says Tricom Computers is a company that sets up local area networks and offices. In setting up a network, consultants need to consider not only where to place computers, but also where to place peripheral equipment such as printers. Peripheral equipment is considered something that is on or near the edge or boundary of something, such as speakers, external drives. Those are other types of peripheral equipment. Tricom typically sets up local area networks of computers and printers in square or rectangular offices. Printers are placed in each corner of the room. The primary printer A serves the first 25 computers, and the other three printers B, C, and D are assigned to other regions in the room. Below is an example. Okay, so the primary is printer A, and then we have other printers B, C, and D in other areas of the room, and it says that A serves 25 computers. So 1, 2, 3, 4, 5 in each column. 5 columns, 5 times 5 is 25, so that would be 25 little dots in there. If each dot represents a computer, how many computers in this room will be assigned to each of the printers? So let's start with printer A. We already know is going to have 25 computers. Printer B, how many computers is printer B going to serve? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many is C, printer C, going to serve? Let me tilt this a little bit. Can we see the yellow? Yeah. Printer C is going to serve 1, 2, 3, 4, 5, 10. Don't believe me? Count the dots. Printer D. Well, I only see 4, so it's going to service 4 computers. What is the total number of computers in the room? Describe 2 ways to find the total. Okay, well, one way is I know that if I add up these numbers, that would represent all of them. So 25 plus 10 plus 10 plus 4. So 25, 35, 45, 46, 47, 48, 49. So that would be 49 computers. There's one way. Another way would be to just count all the dots. 1, 2, 3, 4, 5, 6, 7 in each row, and there's 1, 2, 3, 4, 5, 6 rows. So, 1, 2, 3, 4, 5, 6, 7 rows. So 7 in each row, and there's 7 rows. 7 times 7 is 49. So those are the 2 ways. All right, next page. That's weird. Okay, next page for real. All right, another example of an office in which the Tricom installed a network had 9 computers along each wall. The computers are aligned in an array with the number of computers in each region determined by the number of computers along the wall. Okay, so there's 9 on each wall total, and it's broken up into different regions. So the technician claimed that since 9 equals 5 plus 4, the number of computers in the office could be written as an expression using only the numbers 5 and 4. Is the technician correct? Well, let's see. We know that 5 plus 4 equals 9, right? So there's 9 computers along that wall. And 5 plus 4 up here also equals 9. So there's 9 computers on this wall. So yeah, that's about right. It would work. It's describing the 9 computers along each wall. So yeah, yes, that works. Yes, that works because 5 plus 4 equals 9, pretty much. All right, number 4, show another way to determine the total number of computers in the office. Well, let's see. We know that this is a 5 by 5, right? So just in this region, 5 times 5 is 25. Plus, we could add up what's in the next region. This is a 4 by 5. So 4 times 5. And then we have this region down here. Whoops. It's 1, 2, 3, 4 on that wall. 1, 2, 3, 4 on that wall. We know 4 times 4 is 16. And then this last region down here. We know that there's 4 along that wall and 1, 2, 3, 4, 5 along that wall. 5 times 4. Okay. Well, we know that 5 times 5 is 25, plus 4 times 5 is 20, plus 4 times 4 is 16, plus 5 times 4 is 20. What does this add up to? 25 plus 20 is 45. 45 plus 16 is 55, 61, plus 20 is 81. Just making sure I did that math right. Okay, so now it says rewrite the expression 5 plus 4 times 5 plus 4 using the distributive property. Okay, so if we're going to have 5 times 5 distributing plus 5 times 4 plus 4 times 5 plus 4 times 4. And look what we get. 5 times 5 is 25. 5 times 4 is 20. 4 times 5 is 20. 4 times 4 is 16. So we pretty much get the same thing that we got up here. Okay, and we'll skip number 6 because I think we get it. We get the idea. We're basically just using the distributive property. We're just multiplying. Why? Okay, I fixed my paper situation. That's all done. All right, number 7. So it says the office to the right has 8 to the second power computers. Fill in the number of computers in each section if it is split into a 5 plus 3 quantity squared configuration. So what they mean by that is we're basically finding out how many computers are in each section. So notice there's no dots this time. So we got to do the multiplication. So in this first region, it's a 5 by 5. 5 times 5 is 25. In the next region, this says that this wall has 3, but this wall has 5, so that means this one opposite it should have 5, and 5 times 3 is 15. Then this bottom region, I know that this side is 5, so the side opposite must be 5, and the side is 3. 3 times 5 is 15. And then this last region right here, well, if this side is 3, then opposite it is also 3. And if this side is 3, then opposite it is also 3. 3 times 3 is 9. You like all my rainbow colors? Okay. What is the total number of computers? Describe 2 ways to find the total. So here's way 1. How about we just add up all these numbers? 25 plus 15 plus 15 plus 9. Okay. I know 15 and 15 is 30. 30 plus 25 is 55. 55 plus 9 is 64. So that's way 1. Way 2, well, didn't they say that it was an 8 by 8? So can't we just do 8 squared? What is 8 squared? Oops, you guys can't see. 8 squared is 64. Check. Both the same. So, different ways to multiply and still get the same answer. For each possible office configuration below, draw a diagram like the one next to item 7. Label the number of computers on the edge of each section and determine the total number of computers in the room by adding the number of computers in each section. Okay, so we need to make a box for each of these. So letter A. So we're going to have, it's a 2 plus 3 quantity squared. So we're going to have a 2 and a 3 on one edge and a 2 and a 3 on the other edge. Okay, 2 times 2 is 4. 3 times 2 is 6. 2 times 3 is 6. And 3 times 3 is 9. Kind of like a Punnett square, like in biology, when you're figuring out genes, you know, dominant versus recessive, that type of thing. Same sort of idea. All right, so if we add these all up, we'll get 25. Okay, and if we do it this way without doing a graphic organizer, we know 2 plus 3 is 5, and 5 squared is 25. So notice how we get 25 no matter what, as long as we're doing it right. Letter B. Let's try the graphic organizer on this one. So it's 4 plus 1 quantity squared. So we're going to have a 4 and a 1 on one edge and a 4 and a 1 on another edge because it's squared. 4 times 4 is 16. 4 times 1 is 4. 1 times 4 is 4. 1 times 1 is 1. And if we add these all up together, 16 plus 4 is 20. 20 plus 4 is 24. 24 plus 1 is 25. And over here, if I just follow order of operations, 4 plus 1 is 5. And 5 squared is 25. You guys seeing the patterns? All right, next one. This time we have 3 plus 7 quantity squared. So we're going to have a 3 and a 7 on one edge, and then a 3 and a 7 on the other edge because it's squared. So we need 2 edges. 3 times 3 is 9. 7 times 3 is 21. 3 times 7 is 21. 7 times 7 is 49. Let's see, 49 plus 21 is 70. 70 plus 21 is 91. 91 plus 9 is 100. And then using order of operations, 3 plus 7 is 10. 10 squared is 100. It's nice when there's multiple methods to basically double check our work and make sure we're doing this right. All right, turn the page. Making sure I have the right page this time because I didn't before because it printed out weird. All right, page 62. Number 10, it says TRICOM has a minimum requirement of 25 computers per installation arranged in a 5 by 5 array. Some rooms are larger than others and can accommodate more than 5 computers along each wall to complete a square array. Use a variable expression to represent the total number of computers needed for any office having X more than the 5 computer minimum along each wall. Okay, so one technician said that 5 squared plus X squared would be the correct way to represent the total number of computers in the office space. use the diagram to explain how the statement is incorrect. So that means that this is wrong, okay? We need to use this graphic organizer to show that it's wrong. Okay, well, let's just do what we did before. This square right here is a 5 by 5. 5 times 5 is 25. This rectangle up here is an x by 5. 5 times x is a 5x. Just because there's a variable in there doesn't mean we do anything different. Down here we have a lengthwise rectangle, and it's an x by 5. So x times 5 is a 5x. And then we have this little tiny square right here, and it's an x by x. X times x is x squared. So this is definitely going to be a lot more than a 5 squared plus x squared. So it should be x squared plus 5x plus 5x. Those are like terms, so we can add them together. They make 10x plus 25. So what's the difference between this and the technician's incorrect answer? Well, the only thing I see that's different is it's missing a 10x. So the technician, because we have to explain how is it wrong, the technician is missing the 10x. Okay. Number 11, write an expression for the sum of the number of computers in each region in item 10. Well, we already did that. We got it to be x squared plus 10x plus 25. Then number 12, it says for each of the possible room configurations, determine the total number of computers in the room. Okay, so we'll use the graphic organizer thing. So we have a 2 plus x quantity squared. So it means we have a 2 and an x on the top edge and a 2 and an x on the left edge. And then we just have to multiply them like a Punnett square. 2 times 2 is 4. X times 2 is 2x. 2 times x is a 2x. X times x is x squared. And then we'll just combine like terms and write it in standard form. So the first term would be the x squared because that's the biggest degree. 2x plus 2x is 4x. They were like terms. And then a positive 4. So there's letter A. I won't use yellow because that's going to be too light. X plus 3 quantity squared. So we're going to have an x and a 3 on one edge, an x and a 3 on the other edge, and then multiply them. X times x is x squared. X times 3 is a 3x. 3 times x is a 3x. And 3 times 3 is 9. So that'll be x squared plus the like terms 3x plus 3x is 6x plus 9. Aren't these not bad? Like, that's pretty good. X plus 6 quantity squared. I'll make it a little bit bigger. Just because if I have the room, I'm going to use it. So x and a 6, x and a 6, because it's x plus 6 quantity squared. I feel like I have a lisp all of a sudden. All right, so we're going to have x times x is x squared. X times 6, 6x. 6 times x, 6x. 6 times 6, 36. So x squared plus 6 and 6 is 12, so 12x plus 36. So it's funny how we're still using those adding skills that we learned a couple lessons ago. All right, next page. Page 63. The graphic organizer below can be used to help arrange the multiplications of the distributive property. It does not need to be related to the number of computers in an office. For example, this graphic organizer shows 5 times 7 equals 3 plus 2 times 4 plus 3. So it just broke up the 5, broke up the 7, and we know that 4 times 3 is 12, 4 times 2 is 8, 3 times 3 is 9, 3 times 2 is 6. And when we add these up, 12 plus 8 is 20, 20 plus 9 is 29, 29 plus 6 is 35. Well, that's the same as 7 times 5, which is 35. Okay, so number 13, it says draw a graphic organizer to represent the expression 5 plus 2 times 2 plus 3. Label each inner rectangle and find the sum. Okay, so now they're having us use the same numbers because 5 plus 2 still adds up to 7, and 2 plus 3 still adds up to 5. So they're just having us break it down by different numbers, but they add up to the same thing. So if they add up to the same thing, that means it's still 7 by 5, so it should still be 7 times 5 is 35. So let's check that out. 2 times 5 is 10, 2 times 2 is 4, 3 times 5 is 15, 3 times 2 is 6. See, 10 plus 15 is 25, 25 plus 4 is 29, 29 plus 6 is 35. It's working. All the patterns. Draw a graphic organizer to represent the expression 6 minus 3 times 4 minus 2. Label each inner rectangle and find the sum. Now there's minus signs, so how do we do that? Well, the first one is a 6 minus 3. So we have a 6 and a negative 3. The other one is a 4 minus 2. So a 4 and a negative 2. That's how you do it. 6 times 4 is 24. 4 times 3 is negative 12. Negative 2 times 6 is negative 12. And negative 2 times negative 3 is a positive 6. Well, let's see. 24 minus 12 is 12. 12, oops, that wasn't a 24. That should have been minus 12. If we were in class, someone would have pointed that out. All right, let me start again. 24 minus 12 is a 12. 12 minus 12 is 0. 0 plus 6 is 6. Which makes sense because 6 minus 3 is 3. 4 minus 2 is 2. And 3 times 2 is 6. And then we'll skip number 15 because I think we get the idea. Turn the page. On page 64 now. So it says you can use the same graphic organizer to multiply binomials that contain variables. So we could use the same method. The following diagram represents x minus 2 times x minus 3. And for as long as you guys need to use a graphic organizer, use it. It will help you collect your data together so that it's easy to organize. Okay? So we have x minus 2 times x minus 3. X times x is x squared. X times negative 2 is a negative 2x. Negative 3 times x is a negative 3x. And negative 3 times negative 2 is 6. Okay. So it says use the graphic organizer above to represent the equation. Label each inner rectangle and find the sum. I went for it already. We already labeled each inner rectangle. Now we need to find the sum. So the highest degree is x squared, so that's the first term in standard form. And then we have like terms here, a negative 3x and a negative 2x add up to negative 5x, and then a positive 6. So this is what it adds up to. And we just multiplied two binomials. Multiply the binomials in item 16 using the distributive property. What do you notice? Now this is a method that this is where I need you guys to end up, so that you don't have to draw a graphic organizer every time. But once you get comfortable stepping out of that graphic organizer zone, you're going to be here. All right, x times x is x squared. X times negative 3 is negative 3x. Negative 2 times x is a negative 2x. Negative 2 times negative 3 is a positive 6. Combine like terms, and we get x squared minus 5x plus 6. So we better get the same thing, and we did. Okay. I want you guys to end up here, but if you need to use a graphic organizer to multiply these for now, that's totally fine. You're learning how to do it. That's okay. All right, but from here on out, I am going to be using the distributive property. Determine the product of the binomials. Okay, so we have x minus 7 times x minus 5. There's not a whole lot of room to do these, so I'm going to do these over to the left. Start with letter A. X minus 7 times x minus 5. And you know what, just for learning sakes, we'll do one with distributive property, one with a graphic organizer, so we'll alternate. Or you know what, I'll do the first 3 with a graphic organizer. Sorry, I keep changing my mind. I'm a girl, it happens. Us girls, you know, we tend to change our minds. Sometimes the boys do too, but it's more of a female trait. All right. So one of these is an x and a negative 7, and an x and a negative 5. X times x is x squared. Negative 7 times x is negative 7x. X times negative 5 is a negative 5x. And negative 7 times negative 5 is 35. Okay, so this is going to equal x squared, so that's my highest degree. Negative 7x minus 5x is a negative 12x. And then a plus 35. Letter B. X minus 7 times x plus 5. So I have an x and a negative 7, and an x and a positive 5 this time. X times x is x squared. X times negative 7 is negative 7x. 5 times x is 5x. 5 times negative 7 is a negative 35. Okay, so I'm going to get x squared, and then negative 7x and a 5x add up to negative 2x, and then minus 35. So see how similar they are, yet how different their answers are. A sign can change everything. So be careful about that. Those are little details that we got to make sure we're paying attention to. Letter C, x plus 7 times x plus 5. Okay. All right, so I have an x and a 7, x and a 5. X times x is x squared. X times 7 is 7x. 5 times x is 5x. 5 times 7 is 35. So then this one is x squared plus 5x plus 7x is 12x plus 35. Notice how this answer is very similar to 18A. The difference is the middle term is negative there, and it's positive for here. Letter D is x plus 7 times x minus 5. And now I'm not going to use the graphic organizer anymore. I'm going to just use the distributive property. I'm going to FOIL it out. So first, x times x is x squared. And then outer, x times negative 5 is negative 5x. And then inner, 7 times x is positive 7x. And then last, 7 times negative 5 is negative 35. We can combine like terms. So that'll leave us with an x squared. Negative 5x plus 7x is a positive 2x. And then minus 35. Easy peasy. All right, letter E, I'll go ahead and do it over here since I ran out of room there. So first, 4 times x is a 4x squared. 4x times 3 is a 12x. 1 times x is just an x. And 1 times 3 is a 3. So this adds up to 4x squared plus 12x plus 1x is 13x plus 3. And then last but not least, letter F. Distributive property. So first, 2x times 3x is a 6x squared. 2x times 2 is a 4x. Negative 1 times 3x is a negative 3x. And negative 1 times 2 is a negative 2. So this is going to equal 6x squared. 4x minus 3x is a positive 1x minus 2. All right. Examine the products in item 18. How can you predict the sign of the last term? So the sign of the last term, well, if we just multiply the constants, look at letter A. Negative 7 times negative 5 is positive 35. Negative 7 times positive 5 is negative 35. Positive 7 times positive 5 is positive 35. Positive 7 times negative 5 is negative 35. Positive 1 times 3 is 3. Negative 1 times 2 is negative 2. So if you multiply the constants together, that's how you can predict what the last term is going to be. So multiply the constants. That's how we can predict what that last term will be. I can't turn my page. All right. So this is where your homework is at. So we're on page 65. So your assignment is going to be on this page, numbers 24 through 36. Okay. And there you go. Please make sure you use a separate sheet of paper because you won't be able to fit all the work on here. Remember, to get credit, you have to show work. So either graphic organizers or showing distributive property and then combining like terms. Okay, it's up to you. Have a good one.